Right. This is lecture A, Free Energy Design Principles, Active and Passive of Facades. And when we talk about it, this is about opaque or transparent components. I'm going to show some samples of implementation. Opaque components. We are aware of this building physics set where we talk about the thermal transfer resistance, the resistance of material against transmission of energy called R. And that's a combination of the solid part, which is the material itself, the thermal conductivity resistance of the material, plus the two boundary layers, the air layers, which are kind of insulating as well. We see the energy coming from the inside, convection, radiation impacting the surface, transmission to the outside, and then radiation and convection distributing the energy to the outside. The lighter this material is, the more it is resistant, the more the thermal conductivity is limited. So air, light materials, less energy can be transported. Steel, aluminium, concrete, solid structures, energy can be transported a lot faster, which brings us to the situation that for thermal resistance, we need to reduce the energy to be transported. So the lighter we build, the better as a result. When we think about positioning the thermal barrier, the red line, it's either at the outside, then main structure, for example, is at the inside, or main structure is at the outside. But if this is combined in one line, we see the insulation, the light structure, defending the energy losses close to a structural component, which will be a heavy structure, concrete, for example, where we result in thermal losses by the material itself as a setting. When we define this down into the different types of construction, here we see a single shell construction, solid single shell construction. We see quite straight line of transmission of energy in this setting. This becomes different if we go to solid structure and insulation, and then the insulation being the lighter part actually decreases transmission of energy, while the solid part keeps it in a less steep angled line. If we go to the opposite setting of insulation at the inside, we can assume inside needs to insulate a lot, and then the outer solid part allows transmission in a simpler way because it's more heavy material. And this one as a ventilation, the cavity actually is in this part, so ventilated facade with then insulation and then the solid structure at the inside. We see the steps in this curve as a setting. Opaque. Now, transparent components, mainly glass, so insulated glass units, IGUs. This is a double glass unit or maybe a triple glass unit if we had another layer of glass. The plane, some coatings, a spacer, the distance, a sealant, which keeps that whole part airtight as a setting. And to optimize the heat losses, to minimize the U value, the number of glass panes can be increased. We may have a gas at the inside which reduces the transmission of air. We can have some coatings, which is the red dotted line, which helps to reflect temperature to the inside, or we can discuss the quality of the window itself, which is not the glass plane, but the window itself. When we do the same for the summer situation, we may need to consider a reflection of light at the glass plane itself. We need to think about absorption. There may be also a coating. Now it's at the inner layer of the outer glass pane, which helps to reflect, and then obviously heat input, the G value of the heat input is still active in this. Thermal insulation for sun protection can be performed in different ways by reflection, absorption, reduction, selection, and transformation. Transformation here into heat as a setting. And when we think about how to deal with that in our buildings, either sun is getting into it without any projection, or we have some horizontal shading or some inner shading, which still allows a lot of energy to get into. Sun protection within the glass plane, similar to that one, or sun protection at the outside, which hopefully reflects most of the part, and by that creates the best G value of 0.8, so 8% of the sun being placed at the outside. Some samples of, say, this active-passive energy design, which could be added. We may think of adding energy collectors on passive facades. So seeing these energy collectors, the glass tubes with some water inside being boiled, and that delivering energy to the inside as the one setting, or this system, which I like a lot, the Trombowall system, where we have a transparent insulation at the outer layer, a cavity in between, and then the solid structure at the inside. And in different situations, so wintertime, the sun directly hits the inner surface, while summertime, the sun is mainly reflected from this insulation, which creates a certain temperature at the inside, and that temperature at the inside, for example, in wintertime, can then be used for an opening to the inside, to the room. Trombowall as a setting. Here we see the angles of the sun in summer and in winter hitting our surface. But we also can consider this one as an active shading or active a kind of an active energy design principle by adding a natural shading. And if this loses its leaves in winter, it may even allow to have additional sun performance at the inside. I finished this one with the typical announcements for the literature, which we did on this, and the comment, this is a Delft Darmstadt Munich facade education project.